In order to be able to move our discussion along of solving equations, open things up a little bit more and have some more practical, well, it's kind of tough to see, but practical use for different kinds of equations and, well, things that we've come across that we said previously we aren't going to worry about. We need to introduce, basically, we would need to say we're going to create more numbers based on stuff that we've seen but said we weren't going to do anything with, and that's the square root of negative numbers. When we talked about it before, we said, no, we're not going to do that. We're going to now expand our horizons beyond just those real numbers that we've been using, and we're going to create some more kinds of numbers that come from these square roots of negatives. So what that means is that the simplest version of the square root of a negative number would be the square root of -1. So we want some sort of corresponding number here that kind of fits with a number 1, but ties in with these square roots of negatives. And so we're going to call that I. If we've been working with real numbers and now we're going to create stuff that we didn't have, then that would be imaginary. So this is basically like saying we have an imaginary one. So I. And then we can go ahead and say, all right, now if I take 2 of those, that'd be 2i. And if I take, -4 of them, -4i. But this gives us now a way of expanding the numbers that are at our disposal, which ends up, though these are called imaginary right now, it does end up giving us some very useful practical things when we get far enough along into the maths and sciences. But for right now, we are worried about saying, how does this stuff work out? What kind of arithmetic do we have with these imaginary numbers? What else can we do with them? So, first of all, just kind of getting acclimated to the idea that we can now take square roots of negative numbers. When we do that, what we have to do is we have to split off the square root of -1 part from whatever other square root business is happening. So square root of -81. We're going to take the square root of -1, we're going to peel that off as its own little separate piece from the rest of that square root. Well, the rest of that square root ends up being something much more familiar to us. And then that square root of -1, we said we can very simply call that I. So this gives us a way of trying to shorthand things rather than using 3 symbols, a square root, a negative, and whatever else we might have to have. We can just use 1 symbol, an I, and any other extra number that goes in front of it. For the next example there, the square root of -20, we want to use the same sort of idea of breaking apart that square root of -1, but in this particular case, we also have the extra issue that the square root of 20 does not automatically have a nice answer. The square root of 20 needs to be further broken apart as a square root of 4 times the square root of 5 times that square root of -1 that we already broke off. And the square root of 4 does have a nice answer. The square root of 5 does not. And the square root of -1 can be replaced by I. Now, one of the other options that you might see sometimes, the I, some people like to have at the beginning. The one thing that you will never see, the I will never get buried in the middle of a number and a square root. We won't bury it because that makes it easier to overlook. So we don't have a 2 followed by an I followed by a square root of 5. The I is either going to go at the back end or the front end, never stuck somewhere in the middle where it could be lost. As always, we want to make sure that we're careful about working with the negatives. The negative that's underneath that square root is dealt with separately. The negative that's out in front is dealt with separately. They do not end up, in this case, working with one another. That square root of I gets square root of -1 gets replaced with the letter I. The square root of 36 has a nice answer. the negative out in front stays sitting out in front. We're eventually going to do arithmetic, which means eventually we're going to get to multiplying. So one of the nifty things that we've never seen with any other numbers at this point is the basis behind this side note here. Let's bring up the entire thing. I has a very curious sort of property that when I start using powers, it turns out that as I simplify things and continue to use powers, I go in a circle. Every fourth power repeats itself. Power of 1, 1 plus 4 is 5. 5 plus 4 is 9, so a power of 9 would have this same answer. 9 plus 4 is 13. Power of 13 would have that same answer. Power of 2 plus 4 gives me 6. I with the power of 10, I with the power of 14. Those would have the same answer, -1. I to the power of 3, 3 plus 4 is 7, 7 plus 4 is 11. I to the power of 11 would have that same answer. I to the power of 15. I to the power of 19. Power of 4 plus 4 give me 8. Power of 12, power of 16, power of 20, power of 100 would all have the same answer. That's a 1. Very curious sort of thing. And while you might or may not have a homework problem that uses this kind of cyclic behavior, it's at least worth noting because we've never seen that with any other number that we've ever come across to date. This bad boy just sits there and recycles. I, -1, -I, 1. I, -1, -I, 1. I, -1, -I, 1. Just loops through those again and again. So, curious things that happen are worth noting for simply the possibility that they happen elsewhere and are eventually useful to us. Now those are imaginary numbers by themselves. Imaginary numbers have the I, they have a number immediately in front of it, they might have a positive number or it might be a negative number. But what we can do now is take those imaginary numbers as well as all those real numbers that we've been working with, and we can go ahead and put those together and form what we would refer to as a complex number. A complex number has two separate pieces to it. So a real number piece that comes first. It's got an imaginary number piece that would come second. And so that gives us now a much, much larger pool of numbers to work with for working problems. And specifically, that's going to come up very shortly in solving equations. 2 plus 3i. The first part is the real number part, 2. The second part, the part that has the I on it, that's the imaginary part. 5 minus 4i, likewise. Every real number can also now be considered as a complex number. So all the real numbers that we've been working with fit in this larger pool because they can all be viewed as complex numbers. And all those imaginary numbers that we just introduced can be viewed as complex numbers also. So we have the real number pool, and then if we get out of that and step off to the side, what we have is a much bigger pool that incorporates the real number pool and is much, much larger, having all of the real numbers, all of the imaginary numbers, all of the complex numbers. Excuse me, we've got a lot more to work with. So now we're in a position where we can more thoroughly talk about the arithmetic that comes about from these complex numbers, which means we're hitting the basics, adding, subtracting, multiplying, and dividing. Adding and subtracting, thankfully, are going to, once again, use the ever-present like terms idea. where we're talking about real part with real part, imaginary part with imaginary part. So using a little color to highlight how this is working out, we've got our real parts in blue, 1 plus 2. We've got our imaginary parts in green, negative 2i plus 3i. And so when we simplify each of those pieces, we get our real part in the answer, 3, and the imaginary part in our answer, plus 1, la-di-da. Another example, just to, again, nag ourselves with having the subtraction in the mix and knowing how important it is for us to keep an eye out for that sort of thing and be careful about distributing that subtraction through. So distributing that subtraction through means that we would have the 4 plus 5i minus 7 plus 7i. Our real parts are a 4 and a minus 7. Those will come together and give us a minus 3. Our imaginary parts are a plus 5i and a plus 7i. Those will come together to give us a plus 12i, and there is our answer. Multiplying. It might not surprise you, since we're looking at these complex numbers and they are essentially binomials, that the multiplying is going to work in much the same way that we've seen in the past, where we can distribute, whether that's distributing a real number or an imaginary number. But in the worst case scenario, if we have a multiplication problem with two complex numbers, that is essentially a binomial times a binomial, which means that, yet again, we can FOIL. So let's go ahead and run through those. You can see that the distributing problem there that starts out having the 5 out front times the real number part, the 5 out front times the imaginary number part, and that automatically works out to give us the normal looking answer that we would have for a complex number. In this second example of multiplication, we've got a 3i out front that we're distributing. And so that means that we've got, as it happens, the imaginary part that ends up appearing at the front. Well, that's a little unusual, and so we're going to need to reformat our answer here before we decide that we're done. Specifically, the 3 times the 2 gives us a 6, and that has an I. So there's our imaginary part. That's coming first. That doesn't happen with our normal notation for complex numbers. For complex numbers, we're expecting to have the real number part first. So we're about to get an answer that is not quite properly formatted. Excuse me. The 3 times the 7 gives us 21. I times I gives us I squared. Now we've got the little note in red there that says, let's not forget I squared is equal to negative 1. And so this means that we can replace the I squared. Well, wait. Since our complex numbers are supposed to start out with a real number part, the 21 times the negative 1 isn't supposed to be at the end. It's supposed to be at the beginning of our answer. So we're going to have to actually rearrange that. Instead of a 6i followed by a minus 21, the correct formatting needs to have the negative 21 first, followed by a plus 6i, because our normal complex number notation has the imaginary part as the second part, the second term. So real number part, real term, imaginary number part, imaginary term, they have to be in that order. And in fact, our directions might specifically require that, but that's the standard. We have to follow that standard. So we've got to make sure that we are keeping an eye out for that sort of thing. Now, moving on to the FOIL problem. First times first, 2 times 3. Outer times outer, 2 times the negative 4i. Inner times inner, the 5i times the 3. last times last is the 5i times the negative 4i. 2 times 3 is 6. 2 times negative 4 is negative 8. That's got an I on it. 5 times 3 is 15. That's got an I on it. And 5 times negative 4 is negative 20. I times I is I squared. We can go ahead and combine those I terms together so that we would have a plus 7i. We can also replace the I squared with a negative 1. And that means that what we would have going on here would be, momentarily, a 6 plus 7i plus 20. One more little bit of combining like terms, as well as making sure that we get the proper arrangement for our answer. The real number part has to come first. 6 plus 20 gives me 26. That is the real number part, and that has to come before the imaginary part plus 7i. So yes, a little bit of extra consideration here as we are working through things. However, not too awfully bad for us to keep track of. The nice thing, at least, is so far our arithmetic procedures all match up with what we have already seen and should hopefully be pretty skillful at accomplishing. Now the dividing ends up coming back to that phrasing that we saw back with our radicals, because again, remember that the I comes from radicals. I is a square root of negative 1. So we can bring back that phrasing, rationalize the denominator, which again would mean that we want a nice denominator. This time we want a denominator without any i's appearing, without any complex numbers appearing that have the I. We want just a straight up real number denominator to appear in our answer, because the I stuff relates to roots, and the roots have this important sort of relationship with conjugates. We're using the conjugates again, and so with this example here worked out, foiling out the top, foiling out the bottom, replacing the I squared with a negative 1, combining all those like terms, and this has just that one extra annoying little dimension of we have to have the proper format for our answer. So the 4 on the top has to have its own 13 on the bottom so that the real number is separated from the imaginary part, which would be the 7 on the top with its own 13 on the bottom, and the I showing up either in front or behind. We have to have them split up like that, and if we don't, again, we could be penalized for not having the appropriate complex number format for our answer. A little side note here, if we take a look at a generic multiplication problem with conjugates, what we actually find is that we've got a real quick relationship that we can use if we would like to. So this gives us maybe a little extra speed in working through things. For instance, here in this next example, the conjugate that we would want to use is again the conjugate of the original denominator. So we want to multiply on the bottom by, take the first term, take the second term, change the sign in between them, 3 minus 4i. If we do that on the bottom, we must do the same thing up on the top. In order to work things out more quickly here, for the denominator, we can use that formula idea that we've just seen. If we take the real number part and we take the imaginary number part without the I, and we go ahead and square those, then we can get a much quicker answer for the denominator piece. What I'm referring to here is if we take the real number 3, square that bad boy, we take the imaginary part, we drop the I, that means 4, square that bad boy, add those two together, that's going to give us very quickly the denominator that we need. without having to work through the FOIL steps of all that. Distribute on the top. Simplify that numerator. 3 squared plus 4 squared gives us 25. According to our official complex number format, the 15 will need to be put over top of the 25 so that it is separate from the other half of our answer, the imaginary half of our answer, which would have the 20 over its own 25. And the I, again, either the I could be in front of that fraction or behind it, in front of the 20 over 25 or behind it. Then, as always, with fractions, we want to make sure that they're reduced, and we can reduce each of those to get our final answer here, 3 over 5 minus 4 over 5 I. So that's the kind of arithmetic that we've got to worry about as far as those complex numbers. Once we've taken care of that, though, the complex numbers are going to show up again in our next video, where we come back to solving equations and now are going to introduce other types of methods than just factoring. And these other types of methods could eventually have roots, whether they're real roots or roots that lead to complex numbers actually showing up. So we're going to see how these complex numbers can immediately begin to show up by moving on to the next topic of solving equations in methods other than factoring.